I'm going to talk about event sourcing, and following on from Daniel's talk, I'm going to give all of my examples in F#, which is a really nice language for working with event sourcing and everything else, really. But we'll keep with the theme of the night. So my name's Andrew Browne. I'm a solution architect at Picnic Software. We've been using event sourcing on a project for more than a year now. We started a year ago with a greenfield SaaS application. And our application deals with creative marketing workflow automation, which, if you throw away all the buzzwords, really is, I think, what a lot of people are probably doing, which is automating business processes, helping users collaborate and share information, the kind of typical line of business applications. It's a lot more exciting than I promised, but at its core, that's really what's going on. And that's what we're using event sourcing for. And our event sourced application has been in production for the last 6 months now, so I now feel like we've got enough experience to actually start talking about it from a real world perspective. And I'm only talking about it, I guess, because the results have been really good. Of all of the code bases in my career that I've worked on for an extended period of time, this is the one that I hate the least, which is my pessimistic view of the world. I think is high recommendation. So I'm sort of going to back into talking about event sourcing by giving an example, which is not from what we're doing at Picnic Software, but a very simple domain idea. I'm going to talk about an emergency room. So a quick refresher for those of you who haven't been to the emergency department of a hospital recently. When you first arrive, you'll speak to a nurse at the triage counter. You'll explain what's wrong with you if that's not readily apparent, and you'll be assigned a triage level. If you're bleeding all over the place, you'll probably be level 1. If you're dead on arrival, you'll be low priority and you'll be assigned to level 6. Levels roughly equate to how long you're going to spend in the waiting room. Registration is next, and that's where somebody else, probably at the next window, will collect some personal details, grab your Medicare number, your address, try and match you up against sort of hospital records, anything else they might already know about you. And then, between these steps, this is where the long wait happens. And at some point, you'll be what they refer to as picked up. And that's when you're actually seen by a doctor, where you get what you came for. And at the end of the process, you're discharged. For the purpose of this, we don't care whether you're discharged to a ward in the hospital or you go home. You're out of the emergency department, and as far as this business domain is concerned, we don't care about you anymore. So, if we think about a very basic sort of database design. So the most naive kind of database design we could come up with to capture this sort of information would be a single table. We've got a primary key for our visit, a foreign key to link off to any other hospital records you might have about you, your current status, the triage level you're assigned, who triaged you, Medicare number, all of those things we talked about in the steps in the process. And the first requirement that comes up that forces us to change this model is we find out that if somebody faints in the emergency room, they get re-triaged, because when people have got a 4-hour wait, their health status doesn't necessarily stay the same. So we take this design and we split off, and we'd have a triage joined table. So we'd split that information off so that as people's triage information changes over time, we can record all of those triage events and not lose any data by just updating the status, because for an emergency room, people's triage levels are very closely tied to reporting and KPIs. You can't just lose that data by just updating the single table. And that process will continue on. We'll work out that the status changes over time, so we need another table to capture status changes over time. So as they're waiting, as they're picked up, so that we know the timings of all of those things for reporting later on. Similarly, where they actually physically are changes over time, and that might be important not just for reporting, but for the applications that people are going to use to manage the emergency room to know where people are. And each of these is sort of driven by partly reporting and partly the application. But the idea is that if all we have is a simple table like this, every time we update data in the table like that, we're actually losing data. So another way of recording this data as it happens that we could use as our storage mechanism is we could, rather than model it relationally, just store serialized events on disk or in a database of what actually happened. So rather than have tables or documents with complicated structures in them, when a patient is triaged, whether it's once or many times, what we store is a patient triaged event. And all we'd be doing is actually taking an object from memory and serializing it to disk as something that we store that doesn't change ever. And so we could record all of the information in our system as a series of events that have happened in the past. So as the system makes each decision, as we enter that the patient's been triaged, as we register the patient, as the patient's moved, we would save all of those into our event store. And this is the idea of event sourcing, is that your primary data model is a store of events, and events are things that have happened in your system in the past. So we're not storing the input to the system, we're not storing the fact that somebody wanted to be registered. Once the system has actually registered the patient, made that decision, that's when the event is stored. Now, just having all the events stored isn't very good to us once we need to build an application on top of it. So what we would tend to do is use that event store as the source of data for building up our application database. Now, we saw a relational model at the start, and a lot of the requirements for that were driven by the needs to report on it later. This database is a little bit different from that. This database is purely there to support the needs of your application. So if your application doesn't care about triage levels over time, you just want to tell the doctor where the patient is, this database doesn't have to store that information. Because what you're able to do is, with your event store as the source of all your data, in parallel to that, build up a separate reporting database to meet the needs of the reporting. So I presume that most of you have dealt with systems where you do have an online transactional processing database and a separate reporting database. But what you find is that your transactional model has to actually have all of the data that's needed for reporting in it. It doesn't just serve the needs of your application. It's also there to collect data for reporting. In this case, that's not so, because all of your data is going into the event store in a way that doesn't change, it's there for all time. And so your reporting database is completely different and have information that you didn't bother projecting out into your normal application database. That could just as easily be an analysis cube or a document database. You can also then use that event store to deliver events directly to users of your application. So if you use SignalR now, you'll have a WebSockets connection. As events happen in real time, and you're recording them as events, you've got a really nice model to say, right, who would be interested in that event that's currently logged onto the system? And you can deliver that data to the right user. It's really important to think of these events are not CRUD events. They're not this data was updated. This patient was registered, so you can make really good business intelligent decisions about where those events might want to go. Similarly, this can really help with your integration with other applications. You've got a really strong idea of what's happening in your application and when. And you can also publish these events out onto a service bus or put them on a queue to integrate with other applications. And really importantly, and something that's really valuable for debugging production applications, is that your event store is the best audit log you're ever going to have. I presume that most of you at some point have done what I've done, where you write the database triggers so that when the row changes, you copy the row to another table. And when you go back to debug it later on or build reports from it, it's really difficult because all you know is that this field changed from there to there and you don't quite know what happened. In this, you're not just storing the data, but you're storing also, it's a particular business event that happened. So you've got a really good audit log. And you can also then, you saw that all of these other systems, the reporting database, the application database, were built from the event store. So at any time, you can always rebuild these models or slight variations of them from the audit log, which is your event store. So that's kind of my sales pitch for event sourcing and why it's nice. At a high level, does anyone have any questions at this point? I'm going to move on to sort of talking about more implementation details and how it actually fits together in a real system. Is everyone comfortable with that? I don't seem too crazy at this point. Okay. All right, so let's go on to talking about how this actually works in a real system. So first of all, there's a couple of event stores in terms of software that you can use. The first one is called Event Store. It's written by Greg Young, and he's got a company based around that, so there's commercial support. And it's its own piece of infrastructure. It runs as a cluster. You'll actually install it on your servers. It's very fast. It's got a lot of features that the second option doesn't have, but you are installing extra infrastructure. Event Store, on the other hand, is an open source project, and it will use another database as the actual storage mechanism. So Event Store will run just fine on top of SQL Server, on top of RavenDB. I think Mongo, there's lots of providers for an Event Store. Because actually saving events is a really simple model, it's not hard to build an Event Store on top of another database. We'll talk more about how the transactions and things work later, but you'll see that it's actually quite a simple model. In fact, Craig, who's not here but is sometimes here, he built his own. I think in SQL Server, just bypassed all those options. He said, what I need is quite simple, and he built his own from scratch. So I'm going to take you through, before I get into the details of how the actual events are stored, I'm going to take you through a very basic data flow of how we get from a user wanting to do something to actually having data in the event store in the application database and being able to run the application. So we start off with our user in their browser down here, and they're going to send effectively a command to the server. So a command is not the event, a command is the user wanting to do something. And we can see, so here we've got our register patient command, we've got our nice F# record type here. And so in the registration, we're capturing the visit ID, the patient ID, the registration time. We often just put a route, we're using server stack, so we often just put a route attribute directly on that command, and that adds it to our REST interface. So from the browser, this is the data that's coming over REST and getting to our server. What happens at the server is we then take this command and decide to either write a bunch of events to our event store. So in this case, it would become a patient registered event. It's now happened. This is the point at which the decision is made. Or we might just return an error straight back to the user. So it's when we're writing to the event store that we decide that the patient has been registered. That's just we'll get to building up the database in a moment. The decision's already been made then. So the database sees this patient registered event and it has to decide how to save that or work with that, but that's happened at this point. So this is where the transaction is. If you're looking for the point where you've got your application, you're deciding what happens and writing it in a transaction to a database, this is where that's happening. And then now we actually project out to our databases. In our case at work, we're using RavenDB. A document store can be a really nice way to have your events because you don't need a lot of the features that SQL Server will offer you. Then a document store can work quite nicely. And we call that sort of projecting from the event store out to whatever database we're using for the application. And then so when the user is actually doing their normal, when they load a page, that's the database they're querying from. So, you know, they want the list of patients currently in the ER. That will come from this application database, not from the event store directly. The event store is really nice for storing a really canonical version of the data and getting our transactional integrity, but it's not great for querying directly. What that does mean, though, is that also you can have different models of database. So we currently just use RavenDB. We've got a complex hierarchical security model, and we're actually looking to have the event store project both to RavenDB and to Neo4j in the near future in parallel, so that our hierarchical security questions can be answered by a graph database, and our normal queries can be answered by RavenDB. And we're able to do that because the transactions are happening over here with the event store, and the other ones are just catching up as they go. Yep. Did that all make sense so far? If anyone's not with me, hold me up and ask some questions as we go. So the next thing is, at the moment what we've talked about is having the event store as sort of this big blob of events, or a whole bunch of events on the floor. We actually add a little bit more structure to them. Not much, but we organise events into streams. So in our emergency room example, we might have one stream per visit. So when Adam turns up to the emergency room, he's hurt his tendon. All of the data about his visit to the emergency room goes into one stream. What streams do is they give events a particular order. So all of the events that happen on a particular stream have basically a version number. Events happen in an order. And this is actually the unit at which we get transactions. So say we've written up to event 3, Adam's been picked up, and he's about to be discharged. When we go to write that discharged event, what we actually tell the event store is, I know all about what happened up to number 3, and I want to write event number 4. If somebody else wrote event number 4 before we wrote it, event store would give us a concurrency exception. If nobody else did, then we know that we had all the state up to that point in time, and we write event 4. So we have a really simple model for guaranteeing the transactionality of our data. So what we don't have is cross-stream transactions. Transactions are always within a stream, and I'll talk about modeling in just a moment. In fact, I'm going to talk about modeling now, sorry. So those of you that have read the Magical Blue Book, Domain-Driven Design, you'll have read all about aggregate boundaries. What we tend to do is design streams along aggregate boundaries because they are where we can enforce that we always, so I'm going to use the word invariant. So when we write to a stream, we can look at the current state of the stream, we can know everything that's happened up to there, and know that as we write, we are the next thing that's happening, and we get our transactional guarantee. So we can do lots of other validation. In that example, we've probably, in the registration example, we've probably looked up the patient ID in the read store. But what we can tell, because it's on the same stream, is that we're not registering the patient twice. This is one of probably the harder things about moving to event sourcing, is that you've got really simple transactions, and they're really easy to reason about, but you do have to come up with a model where you can live with this being the only transaction type you've got. So you do end up shaping your model and what's on what stream to not have too many things on the one stream because you don't want to create extra concurrency exceptions, but you also want to group them in such a way that you can always guarantee the properties of the system that always need to hold true. So this is an example just on their own of what commands and events look like. We are using, sorry, I should have mentioned, we are using F# in production, so all of our event sourcing code is F#. These are record types that Daniel talked about. And our command handlers, and this is a very simple one, I haven't introduced state yet, are really all they're doing is they are taking a command and they are transforming it into an event. So you get a command from the user that they'd like to do, and they're returning an event which will get stored in the event store. The thing that we're missing there is when a patient's triaged, there's probably not a lot of state, there's probably not a lot of validation we need to do. But for other commands, that's not going to be true. And so what we need to do is have a way of looking at not just the events in the stream, but what is the current state of the stream. So imagine the things we might want to know when we're validating commands. We might want to know, hey, has this patient, for this visit, has the registration already been done? What is the current triage level? When were they registered, if they were registered? So you can see these are all option types because the first event may not have the information to give that state. So they'll all start out being none. You can see I've got my empty definition of what the state would look like down the bottom there. So by default, they're not registered. If we don't know the triage level, we don't know the times that they were registered and discharged. And we are building up a library which we're going to open source, and we've used the concept of what we're calling a state builder. Really what this is just a fancy left fold for those people who have done some functional programming. Daniel showed you an example of the reduce function. Really all this is a complicated way of calling that. So what we start out is with empty state, and then we add a bunch of handlers. And all the handler does is look at the current state and the event that's just happened and return the new state. So imagine this is the first event that's happened to a patient on a particular visit. You get a patient triage event come in. We're dealing with this handler here then. The current state is actually going to be empty at the moment, so we start with the empty state, S, and this is that nice record update syntax that Daniel talked about. And so now that they've been triaged, we say, hey, we've got the empty state, but we now have a triage level set. And the same thing happens as we go through each of the events in the stream. As we get the patient registered, then we take the current state. In this case, we will have the triage level, and now we've got that they're registered, and we've got the registration time, and the same for the discharge. So the events are never changing. Once they're written, the events have been written. We don't delete them, we don't update them. We just add events to the stream. And so we've got a really simple model of working out what the current state is just by taking the state before, looking at the event, and getting the new state. One thing that some people are probably going to be asking is, isn't this really inefficient? If you've got lots of things that happen, if Adam's in the emergency room for 8 hours, 12 hours, 24 hours, and thousands of things happen to him, isn't this going to be inefficient? The first answer is actually running those state builders can be quite fast. The second part of the answer is because they are just a left fold over the events and everything is immutable, we can actually store snapshots of the current state. So conceptually what we're doing is building up the current state from the previous state and all the events that happened on the stream. But we can grab any snapshot from any point in time. So say we're at event number, we've got a snapshot from after event number 2, and we're discharging the patient. So number 3 has been written, but it's not as part of our snapshot. All we do is we load the snapshot at event number 2. We know because everything's versioned on the stream that we're at, the snapshot was taken at event number 2. We go back to the stream and say, right, what are the events past number 2? We get event 3. We just run that handler from the snapshot. So we've only run one event, and we're back to having our current state. This one was a really nice example state builder to explain what actually happens. What we found over time, though, is that it's actually much easier to deal with smaller pieces of state. So we've written some infrastructure so that we can actually build smaller state builders, because a lot of the time a particular handler is only interested in a subset of the state. So for instance, the example I'm going to show in a moment is the registration handler. The only state we're really validating there is that this is the first time the registration has happened. So what we can do is we can build a much smaller state builder. This state is just a Boolean value. When we get a patient registered event, we don't care what the previous state was. The patient has now been registered. So that's a less good example for explaining it, but that's the kind of thing we're starting to write as we do more event sourcing, as we end up with smaller pieces of state. For example. All right, so flashing past you earlier, you saw the triage patient command handler. So, first of all, all we have for a particular aggregate really is a sequence of command handlers. And we're actually using the sequence computation expressions to just return a bunch of handlers when we configure our everything. So we've seen the triage patient one. That one was very simple. One that's a bit less simple is the register patient handler. So this one's a full handler. And so as parameters, we take our isRegistered state. We've got some context. Normally there's some context in an application, so that might be who the currently logged in user is. It's something that's not part of the command, but that's sort of always present. So we, in our context, we have mainly who the user is and which client's instance of the application is, those sorts of pieces of data. And then you have the command itself. Now, you won't be able to see this, but the actual type signature of this is, a command handler, just to reiterate, returns a list of events to be written to the event store or an error. So the type we've got here is a choice of either a list of events or basically a list of errors. It's called a choice type. Daniel showed you the option type where you've got some or none. This is very similar to that, except in the none case, we don't just have nothing. We've got a whole bunch of data, which is the list of errors that happened in our application. So this build event function here is sort of what we wish we could write. That we could just have the address, the Medicare number, and spit out an event. But the world is not quite as nice as that. So if we look at our command is going to send in flat data. We don't have our nice little address object on the command. We've got a bunch of strings that are unvalidated that we need to validate and check before we write those as an event. So I'm not going to explain the details of how these things work. I'm only just going to show you what's happening. But I can assure you that the details were all in Daniel's talk. And they're just different ways of combining that. So the first part here is I'm building up a validated address. So similarly to the command handler, this is not just an address. Because we've validated it, it's either an address record or it's a list of errors that were found during validating the address. So the meat of our command handler is that we check that the patient isn't already registered. If they are, then just fail with that error. If they're not, then rather than call build event directly with an address and a Medicare number that haven't been validated, we're using these special operators, and they're the parts that I'm not quite going to explain, but they basically put together the application flow along with the error flow, so that what we get back, if I show you our form, here's one I prepared earlier, is if I hit register with an empty form, I'm getting back all of those errors. So that code you see there, whilst it's validating things, is able to, because of the choice type, encapsulate success and failure at the same time and carry around not just one failure, but the sum of all of the failures that it could get to. And then return the right thing at the end. So that build event in that case wasn't actually called, but because of these special operators, which are really just a way of composing functions together, it was able to instead return me a list of all of the errors. And you'll see that obviously there's all the address errors, but there's also the Medicare number error. So those parameters, all of the address, all contributed, and the Medicare number both contributed errors. And you'll see if I go in to have a look at how validate address works, that all of those fields were also contributing to that error message. And you see I've also called down to the postcode, and that was all getting composed up together. So you've got this really nice code that's dealing with both success and failure in parallel as one pipeline of data. So that's one of the places where, because we've got really explicit commands and events, we can write really pure, neat functions that do exactly what we want to do, and where we're not writing a whole bunch of, often what I find when I'm doing validation in C#, I'll have a, if this thing's not null, then do this with it. In the F# version, I know that it's not null because the type encapsulates that. I've either got a correct address or I've got a list of errors. I don't have an incorrect address. My code won't let me create one. So that's kind of the end of what happens with the actual writing to event store. Does anyone have any questions about that before I move on to building up the read store? Does that all seem fairly straightforward? With Tim? Yep. You mean of the errors, or like?
Say patient comes in, gets triage, then dies, or if maybe discharged to another room or something like that,
Yeah, so I mean, there was kind of a very small example of that, I guess, and it was just an if statement.
Okay.
Really, where I checked that he wasn't already registered. So, in this case, if they were already registered, we just returned an error. We could have just as easily returned a different event. So, what you're doing in these command handlers is basically looking at the current state of the stream and the command that's come in, and then deciding what events to omit or what errors to return. So you've got, does that kind of answer your question?
Before we had it all through that piping operator,
Mm-hmm.
it looked like it was
So it looks like that, doesn't it? Yes. But actually, well, so it depends on how you arrange it. You can arrange it both ways. You could, it depends on when you make the decision about which event to omit. But basically, you can put these things together to get as many errors as possible. That's normally what you're trying to do. So you might do the address validation first, and then always return those errors first. Because if you make the decision based on the address object that you've created, then you're going to actually return those errors before you even get to making that decision. So you might end up, yeah, there's a few more operators in this language that let you do things like that and choose which way to go. And you can always, I mean, Daniel showed a bunch of pattern matching. We've only just started looking at using these operators because they're really nice and clean. But you can actually do all of this with pattern matching. It's just a lot more verbose. So you can do if statements and pattern matching and get exactly the same behavior. It's just that by spending a little bit of time learning operators like this, you get this nice flow where everything's happening in parallel, and you're always encapsulating the idea of failure and success at the same time. So the next thing that happens is we need to actually get an application database. And what that looks like is something we've almost already seen. So we might, I'm going to give a document example because that's the easy example to give, and that's what we're using at Picnic Software. So our document might just be a record type, and building up that document is conceptually the same as a state builder. All we've got is we start with an empty document in the database, or not in the database, and we're getting events from Event Store and updating the document. The big difference here is that these events, whilst the state builders for the aggregates need to only include events that have happened on that stream, when you're building up the database, you've got access to all of the events from the event store that have happened in any of the streams. So you can build composite documents or documents that link related things. You might, for instance, want to, this is an example of updating the visit document, but you might also want to update the patient document to say, right, the patient's at the hospital now or something like that. And so you can have the patient document also capture the patient registered event and say, right, they're already in the hospital now, and maybe the discharge event to say they're not in hospital anymore. So from that perspective, the read model is very similar to aggregate state in terms of conceptually how it works, because they're both doing the same thing. We've got an immutable event store with all of our data in it, and we're just looking at different ways to arrange the current state of that data. Yep. Yep. Mm-hmm. Yeah, no, they definitely can arrive out of order. So basically all we're doing here is that we're just saying, hey, we're interested in the patient triaged event. So they will come in the order that they were in the stream. Yeah, so they come in the order that they happen, not in the order that they happen here. Yes. In fact, all we're doing behind the scenes is a bit of reflection to grab the type as well so that we know what events to subscribe to, and then running a fold over those things. But the accumulator function is switched on the type. It's exactly what's happening. Yeah. But one thing that comes up, I talked before about the fact that transactions are happening over here in the event store. But we still need to ensure the integrity of our read store. We've had some messaging talks here before where we talk about the need for messages to be idempotent. Because we've got streams of events and they're all versioned, we can actually do that in the infrastructure in this case. So if we pop over here, this is once again a Raven example, but you can think of easy ways to apply this to a SQL Server database or whatever other database you've got. Raven's easy because it's actually got a metadata section of the document. And so what we store along with your normal Raven properties is we actually store for each stream that document has had, so for each stream that's contributed to a document, we just store the last event that was written to that document. So obviously there's your normal transaction around writing a document, it either completely wrote or it didn't. If we crash halfway through reading events from the event store, we can simply replay those events, and when we load this document, we might get event 3 again. That's okay, because we've loaded the document, we see that event 3 has already been applied, and we just ignore the event. This gives us something else that's really nice too. If you just deal with Raven on its own, and you want to update 2 documents as the user does something, unless you use put those in the same transaction, there's always a chance. So Raven's not a good example because it supports this, but there's other document databases that don't support cross-document transactions. There's always a chance that the server will crash after you've updated one document, but before you've updated the other. Because our transactions already happened, when we start up, we can make sure that we're completely caught up. And so if one document was updated and the other wasn't, then that event will just get applied to the second document, but it won't get reapplied to the first. And then we also store one more piece of information. This is a particular event store example, but you can do equivalent things with an event store. But basically we store the position that we're up to globally. So an event store, as well as having the streams, gives each event a global position, which is sort of an ever-increasing position. And we simply store that with the read store database. So each database or representation of your data knows how caught up it is with regard to the event store. And so as we've dealt with all of the events before this point, we write that to the database so that if we crash, we load up and we say to the event store, hey, this is the last one I'm completely finished with. Replay me from there and we'll catch up from there. So anything that was missed or half written, we get a chance to double check it and on we go. Which brings me to the next sort of superpower that you gain by using event sourcing, which is the ability to completely rebuild your application databases and your reporting databases. Because all of your data is actually in the event store, you could delete your application databases at any time, so long as you've got a long enough outage window, and rebuild it from the event store, because all of the data is actually somewhere else. So apart from a disaster happening, another time when you might want to do that is when you actually want to change your application database model without writing a bunch of data migration scripts. Because all you do is if you change those state builders that build up the document, you can then just spin up a new database, start from the start of the event store and build that database up. That will take time. We've been in production about 6 months, and on my developer machine, it takes about 4 minutes to rebuild, and I'm sure that will grow in time. But the thing is that new database can be being built with the new model whilst the other one's still live, because it can be an extra subscriber to Event Store and just build up as it goes, and then you switch over to the new database once it's caught up. We will do something similar to this when we move to Neo4j for our security model. We will basically start with an empty Neo4j database, go back to the start of Event Store and replay all of our events and build up the correct graph database based on everything that's already happened in our system. We did something similar as well for reporting. For the first few months, we didn't know what reports users were really going to want. So once they worked out what data they wanted from the system, we built the reports. And we didn't have the experience that I've had many times in the past where we build a report today and we say, right, this report for last week was empty. Even though things happened, we don't have that data, or we weren't able to go through the audit log and recover that data. In this case, our reports that we built 3 months in were actually reports that reported on the data from day one because we had all of that data available to us in a form that was easy to build the reports from. Do we want to talk just briefly about eventual consistency? Eventual consistency is often sold as a feature. 12 months in, eventual consistency is a pain in the butt. I really hate eventual consistency. You can see here, if I go back to our model here, that the transaction happens over here at the event store. This restore database is catching up from the event store as fast as possible, but there's always going to be a time where it's been written to the event store, but not yet written to whatever your application database is. So what I've found is that it's actually not that much of a problem in production. A lot of the times the users aren't quick enough to notice this. These things are happening very fast. But it will be a problem with your testers. Your testers will do things to find holes in your eventual consistency model. It's also a pain now that we're looking at exposing our API to other people. Once people start automating things against your API, these sort of things can show up. So we're combating this a couple of ways, which probably won't scale, but we're talking about probably thousands of users per customer, not tens of thousands. And so you have to think about all of these things, I think, in the context of what scale you're really working with. So at the moment, what we're doing for a lot of requests is that we actually hold the HTTP connection open. All of the web servers now support async, so you're not holding up a thread necessarily. And we actually wait with a timeout for the read model to actually be updated so that users of that part of the API aren't aware at all of the eventual consistency. So although it's there, the users don't necessarily have to be aware of it. As we move on, and I've just talked about having Neo4j and Raven involved, we're actually looking at returning in a header something equivalent to this information so that when a user does a write, when they're next doing a read, they can send that information back to them, and we can make sure we never display them data that's older than their previous write. So eventual consistency is there, and it can be a pain, but there are ways to sort of deal with that, as well as also from your user interface point of view, you can design user interface so that that discrepancy and that small time delay, and we're talking about tens, hundreds of milliseconds in most cases, doesn't really show up. But it's something to be aware of. Next, I want to talk a little bit about testing. And the testing story for a model like this is really nice. So what we saw back there was the command handlers were basically pure functions. They took some inputs and they returned an output. So tests for the event store actually end up being quite boring. They're usually something like this. So I haven't shown the command here, but basically we call that function with our state and our command, and we're expecting this event, and we say, hey, we're asserting that we should get the expected event back out of the function. And because F# has nice record types, equality just works. You don't have to compare property by property. You just do up a new expected event, use equals in your assert, and you're done. And this syntax is really just a wrapper around, we're using XUnit here, but it's really just a nice functional wrapper around those asserts. With pattern matching as well, you can get a little bit fancier. Say you didn't want to compare all the properties, you didn't care. You can see here I've got my equals, and this is an active pattern. Daniel mentioned active patterns earlier. This wouldn't have to be equals. This could also be, in the time case, it could be, within 5 seconds, within a second. You can do all sorts of fancy pattern matching. And I'm doing the same thing now. I'm just really just running the function and saying, hey, my result should be a success that matches the expected event, where the expected event in this case is really a function from an event to a bool that's encapsulating a pattern match. What I'm finding though is that because our command handlers end up being so simple, that's actually not where a lot of our bugs are. A lot of the things that come up are really more in the integration between the event store and the read store, or the queries that are based on that. And so we're looking at ways of being able to test those things as a unit. So one of the weapons that we're starting to deploy is a thing called FsCheck. Has some of you heard of QuickCheck from the Haskell world? So it's sort of a way of turning your test inside out a little bit. So really what you do in the FsCheck case is you declare a property of your code. You can see here, this is not related to event sourcing, this is just the canonical example and saying, hey, I declare that if I take a list and reverse it and then reverse it again, I'm going to get my original list back. So you can hand that function to FsCheck and it will generate a whole bunch of different lists of different lengths with different integer values in them and ensure that that is always true for all of those values. Where we're starting to apply it is in our library we've written test generators that can look at an aggregate and generate random commands to fire at that aggregate. So what this test here is doing is it is looking at the visit aggregate and it's saying, hey, generate me a whole bunch of commands, fire them at the handlers, write those events to our test event store, and then run those commands against the view model. In this case, I'm not actually asserting anything about the view model. I'm just wanting to make sure that there are no errors for anything that gets through the command handlers. So lots of these command sequences will actually be invalid and they'll generate no events. They'll just generate validation errors. That's fine. We're ignoring those. But any events that do get written, we run those against our view model. We saw that code earlier. That was the state builder that was building up the document. I'm going to run this for you now. Did I hand up there? Okay. Did I hand up there? Okay. I've run it already. Hang on, let me run it again. So this is what FsCheck looks like when it's almost finished. Right, great. So FsCheck will run a bunch of different tests all at once. So for that one property, it's failed actually after 2 tests there. And what it says, hey, I prove your property false after 2 tests, and it's given me the data that's sent to basically generate an exception in my read model, and it's given me the line where the problem happens. So if we look here, what we've got is a pickup event followed by a registration event. And we've got basically a null reference exception, which is the bug I put there on purpose. And so what that's telling us is that when you get a discharge event before the registration event, which is not something we'd normally expect, we get an error. And if I pop down here, in fact, I'll show this. Here, doc.registered is an option type, and I'm calling .value on it. Don't ever do that. That's circumventing all of the null checking advantages that option gives you. So basically what FsCheck is telling me here is, hey, I've missed either 1 or 2 things, and probably 2 things. I've got to check for the possibility that they might not be registered, and probably I need some validation in my command handler for discharging to make sure that the patient has actually been registered, if that's a sequence that shouldn't happen. And you saw my is registered state builder, so I can easily do that and add that there. So FsCheck is a really nice way, and can be used from C#, I believe. I haven't tried. I think it's a little bit nicer with the F# types, because F# types all support equality. It's really easy to write those properties of your system, but it's all very doable. I mean, it's .NET code, so you can definitely do it against your C# code as well. So that's my error. And then, like Daniel, I'm going to finish with talking about computation expressions. So in our case, deep within our infrastructure, we've actually written our own computation expression to encapsulate the idea of event stream. So this is just giving you an idea at the end of the power of using F# to do things like this. So you can see we had in the async example, there was the let bang was the special thing. Same thing in all computation expressions. So my computation expression is encapsulating dealing with event streams. And the 2 functions that I'm using here that are special here are read from stream, which is doing exactly what you think it is, reading the events from the stream, And read value is just an encapsulation around the actual deserialization of the event. What this allows me to do is you saw back on my FsCheck, there's no sign of any async here. But this example, this is actually loading up from using a state builder and loading up and calculating the current state from an event stream. This code runs in both that FsCheck test and in our production code. And the way it does that is because of computation expressions, we can actually write two different interpreters for our computation expression. One that's used in testing, and each interpreter, I should say, is about 100 lines of code. It's not a huge amount of code, and it's basically one big pattern match. And so unlike an ordinary mock where you can't really change the outside signature of the code, I've been able to use the same code to load up the current state in our tests without any async. And then I've got a separate interpreter for a computation expression that actually interprets it as an asynchronous function that's actually going off and doing real work when those special operations run, and allow me to be completely asynchronous in our implementation for production. So coming soon, I, with the support of Picnic, publishing a library, but I stopped writing that to write this talk. So it's coming soon, unfortunately. But go and start on GitHub because it'll make me feel good. So parts of it actually are already in production in our app, and parts of it are being put together in a better way than what we're currently doing. And I'm doing things like using this to test the concurrency requirements of our application, because obviously, because I can take async and put it in and out of the application, I can also use the synchronous version to interleave different commands running at the same time and test those scenarios in a deterministic way as well. And I've got here, I presume in the slides I go up on Meetup. So, yep. So I've got a whole bunch of links at the end here. Because the talk, I expect there'll be lots of sort of questions about the details of lots of things in the talk. There's a lot of references at the end here if you go and have a look. I've also pointed out F# for Fun and Profit, which is an awesome site, and talking about how the validation works, different testing links. So really, I encourage you, like, event sourcing has been a huge win for us. I was asking my boss as I was preparing this talk, I was like, how do you feel about it a year in? And he said he wouldn't do it any other way. I was a bit worried that he might say, because it is a lot of work. You have to do your modeling differently. But he said he really couldn't imagine building a system like this any other way, because it just makes you feel so safe that you've got all of the data captured in a really nice way that you could possibly have. And my boss is actually in charge of the backups as well. So it means it's just one thing that he knows he has to back up, and he knows that it's not changing. So last week's backup contains all of last week's backup. There was no update to the database that happened this week that wiped out some of that data. So every backup contains the entire state of the world as it's happened. So that's what I got. Anyone got questions at the end? Andrew? Mm-hmm. Yeah, it finds, so FsCheck, by the way, I've used in the development of the library. We haven't used it very much at Picnic yet. But in the development of the library, it's found all kinds of things that I would have never found. Particularly, I found it's really valuable to write tests that do things like, say, this sequence of things doesn't work, and that normally does pass because you've got a unit test that tests that when it's complete that it works. But it's often very easy to write a property that says, hey, if you've got this valid sequence of things, what happens when it's all done except the last one? Does that state still make sense? And those are the kind of spots where I've often found it'll find strange things. That and sort of special cases, like you're not handling the empty condition properly, you're not handling off by one things. So yeah, I'm always amazed at what FsCheck finds in my code. And occasionally it's things where I just need to exclude that from my list of things to test. But often it's actually things that are potential bugs in my code. So yeah, I've been constantly amazed at what it will find, even on small examples. It's probably horrified at what I find sometimes too.
You've got one of your slides, you had like a triage expression on it with the curly braces. What's that?
Oh, it was on a slide, was it?
May have been the code that you...
Triaged expression.
You go back to the code.
Oh, I think that was just a record.
Oh, okay.
I think I know what you're talking about. That.
Yeah.
Yeah, sorry. Oh, right.
Okay.
Sorry, there was something I didn't mention. What I tend to do is I use the discriminated union to combine. So obviously this part from the curly brace on, that is the actual event, the triage event.
Yeah.
What I actually create, if I show you the code, is that encapsulates all of the events that could happen on a stream. So that I sort of unified all of those different events, and I can know that I've dealt with all of the cases that could happen on a stream in there. So that triage is actually matching up with that there.
Got it.
You've also got a nice short name to refer to things by.
Yeah. It's interesting to know, like, when you've got the pipeline, this event happens, the second, the third, and fourth. What happens if the business turns around and says, okay, we're going to slot in an extra event, after registration release, to take payment, for example.
Yep.
Immediate payment before someone can send over stuff. What happens to the event store then?
Right, okay, so the event store doesn't change, right? What happened in the past is you didn't take payment first. So, the event, sorry, that's something I meant to say and I did. The event store encapsulates the decisions that were made at the time they were made. So, I guess it depends on what you want to do about it. So what we've had is we've had cases where events were, say, missed, or we added new events. And what you'll often do is instead of a database upgrade script, you'll have a time when you decide, okay, there's all these extra events that we need to happen now, and you'll actually insert those as part of the script. If those transactions sort of done and that just didn't happen, then you just need to always have your application database, when it gets built, be able to deal with the fact that those events didn't happen. So the event store stores the facts. The facts of what happened at the time never changes. And depending on what you actually want to, like, it might be that you just want payments to happen from now, and that's sort of fine. You just add an extra event type to the aggregate. The old ones don't have them. But yeah, so it really depends on the details. But I guess the thing is, you don't change the event, or that's not what happened at the time. It might be that you actually change the way the old events are interpreted to update the read model in a different way. So it might be that the registration event is a different thing. And so when you said the old registration event, you deal with that one way. And when you see the new combination of a payment event and maybe a registration event version 2, you deal with that differently. We're using JSON to actually persist all of our events. So as long as any new properties on events default to false, we're sort of fine. Like, things deserialize reasonably nicely with JSON. If you just think about how the events are stored and what they're going to deserialize to, you can often do things that way. But if if there's just some extra data, but the event didn't really change, then you can often do a translation from what's stored to the new event type. If it's actually semantically different, then often you actually need a new event type. And maybe the old events are stored and you deal with them in the read model, but you never actually save those events anymore. Those events don't happen anymore. The business process has changed. Does that kind of get at what you were? Yeah. Hey, Sean.
Where this was talking about after you have to stick in a payment event in the middle, would you alternatively look at like having patient triaged event 2 from now on and just ignore what happened in the past, and then build a different type of sequence from that way? Or do you always go for this backward compatibility so that you can always reinterpret and just ignore those old pieces of data?
It depends on what part of the system you're dealing with a little bit. So from the read store point of view, those imagine you rebuild your read store database, or even just migrate the current data. Like, those events still happen that way, so you always have to deal with those.
Oh, I got that, yeah.
But so I thought versioning was going to be a big problem, and it hasn't come up as often as I thought it would. Like in the example where there's a new event or the process changes, like the payment example, you really just add the new event and you slot that into the process. And new streams include that event and old streams don't. And so long as the read model reflects that, and when your aggregates are building up their current state, they can reflect that. You sort of don't run into too many problems between events. It's more when an event changes to mean something different and you end up in more trouble, and that's when you do end up with the V2 event or the event with a different name that's similar but not the same.
Yeah, but it was the same question.
Oh, sorry, yeah.
Basically.
So we're going to go into event sourcing next week on the greenfield application. Yeah. Yeah, okay, so we're at a couple of gig at the moment. I mean, it will grow over time. It doesn't look like it's going to be a problem for us. If you're storing a lot of data, that's something you might need to think about. But storage is relatively cheap. So it's going to depend. So one thing we're starting to look at is we've got a few bulk processes. And what we're looking at is having those things happen outside of the event store, and then the result of those processes going to the event store, but making sure that the sort of the transitions in there that are really very crud and we don't care about the details after the job is over. Doesn't all happen in the event store, but then the result of that goes into the event store. So yeah, so I mean, it's good. How long is a piece of string? It's going to take however much space your JSON serialized documents take. But how big that is for you at the main is going to depend on what you're storing. So.
Does that for the event store, does the snapshot get stored in there as well?
Right. So at the moment we are storing them in the event store. I'm tempted to actually store them in Raven. From the model, it doesn't really matter because all you do is you grab a snapshot from wherever you can grab it from, and you build up from that. It doesn't really matter where you retrieve from. I'm also looking at storing just snapshots in a cache in memory as well, just to speed things up because it's easy and it's cheap, and the cache is never wrong. It's just out of date, and you know it is because you're good versioning. So you can store multiple snapshots wherever you like. It doesn't really matter. Yeah. But sorry, the actual answer is sorry. It's in the event store.
Presumably you can rebuild from a point in time. You don't have to go from the beginning of time.
You talking about the read store, like the application database, or the snapshots, or
yeah.
You can rebuild from a point in time if you have the database as you wanted at that point in time.
Yeah.
So I guess doing all of this doesn't prevent you from writing data migration scripts. But what it does mean is if you can make your rebuild fast enough or do it offline, you can avoid that and just replay from the start of time and build up the database as it would have been if my restore was written down. So it's an extra ability you've got, but you don't ever have to rebuild it. If you change the shape of your documents or the shape of your tables, you can just write data migration scripts like you do today and keep replaying forward and have a little work.
Alright, we might have to have more questions down at the pub because Claire's going to about to step back.